Hey everyone, welcome to another episode of Conversations with an Astrophysicist. I'm your host, Scott Lewis from knowthecosmos.com, and with me, as always, is our astrophysicist, Dr. Katie Mack from Melbourne, Australia. How are you doing, Katie?
Good. How are you doing?
I am fighting some sort of cold, but we will get through this. I am on
We will.
Sudafed and coffee, so yay.
Okay.
It'll be
Good.
great. And science, and science, so that always helps too.
Science.
So before we get started, I do want to let people know that there are many ways of interacting with us and engaging with us. First off, please share out. I know we just tweeted and shared things out on Google+, on Twitter, on Facebook. So please share that out so we can have as many live viewer engagements going on. I have the Q&A app open on YouTube and Google+, so you can actually ask us a question. We can see it and respond to it live while we're on air. And then you can, again, tweet at us. So I am Scientific Scott right there. And Katie is...
Astro Katie.
Astro Katie, the most followed astronomer in Australia. Boom. So you can do that, and also make sure to subscribe to Know the Cosmos, and this will be up on knowthecosmos.com sometime tomorrow when I sleep and do that stuff. So we are talking about gravitational lensing, and it's been a pretty hot topic lately. As I've been, really involved with the Hubble Space Telescope Hangouts, and so we've seen a lot of that, and there's been a lot out in the news lately. So we wanted to touch on it, but we know that there's a lot of information to cover, so this is going to be part one about gravitational lensing. We're going to split this up into at least 2, maybe 3 episodes to get a good rundown. So
I mean, there are a lot of different kinds of gravitational lensing that we use in astrophysics to learn about the universe, and that we just see in the sky as interesting things. So we're going to talk today about strong gravitational lensing, which is, I guess, what most people think about when they think about gravitational lensing.
Right.
And then, next time we'll talk about some other aspect. But I think that this one is a good place to start, because it's where gravitational lensing is the most important, the strongest, Yeah.
And what we need to know first before we get into gravitational lensing has to do with the little guy you have over there. You brought a friend with you today.
This guy. So gravitational lensing depends on general relativity, which is, of course, Einstein's thing. And actually, gravitational lensing was the first thing that made Einstein famous. So Einstein wrote a bunch of papers about relativity. He wrote, first of all, about the special theory of relativity, which has to do with the speed of light and moving through space and how time changes and stuff like that. And then he worked on the general theory of relativity, which has to do with gravity and space-time and how space-time bends. And the 30-second intro to general relativity is that space-time is in general relativity, space-time is something that can bend, that can be distorted, and basically anything that has mass bends space-time. And so the bending of space-time changes how things move through space. So let me just show you
even you and me, you and I, on a very, very, very small scale, because in the grand scheme of things, when we're talking about natural forces, gravity is pretty weak, so you have to have a lot of mass to really warp it. But we have mass, and so we are able to warp space-time, just not in any real measurable way.
Right. So let me show you a little. So let me show you a little diagram of. Can you see that picture?
Yeah.
Is that okay? So this is a diagram.
Can you zoom in a bit?
I'm
Command
not
plus.
sure.
Maybe?
Let me see. Yeah. Let me see. Is that better?
Yeah, much better.
Okay. Okay. So this is a diagram of the bending of space-time around the sun, where you can see in this picture you have the sun is a massive thing, and usually when we talk about the bending of space-time, we use an analogy where you have like a mass on a rubber sheet, that kind of thing, where you make a dent, and that's not a perfect analogy. You have to kind of think one dimension up. So it's more like space-time is like being gathered around an object in 3 dimensions. But you can kind of visualize it this way. And so let's say that there's a star that's somewhere behind the sun relative to the Earth. So we're on the Earth and we're looking, and somewhere behind the sun, blocked by the sun, is a star at position A. Okay, so right there. And the light from that star goes out in all directions, and it's all blocked by the sun from our perspective. But because space-time is bent, one of the light rays that would have otherwise shot right past us is bent around the sun because it's trying to travel in a straight line, but space-time is not flat. And so it's curving through space-time because space-time is not flat.
So it is still going in a straight line, but
from its perspective,
space-time itself is not, allowing it to. It's curved, so it is going straight. It's just that the trajectory it's on is being warped. So light itself is still going in a straight line. It's just that the medium. That's long term. Don't want to say medium because that gets into a whole nother thing.
Yeah, that's a little
nonsense.
Yeah, it's a different thing. But anyway, so as the light is traveling, so the light gets bent, and so from our perspective, we think that it's in a different position. So we just draw that straight line, and so we see it as though it's at position B if space-time were flat. And so we see that sort of that change in position, and that's what gravitational lensing is. And this is how
isn't that how Einstein was proven correct, right?
Yeah, I mean this was the first big verification of general relativity. So in 1919, Einstein made this prediction about how something would be shifted in position by the bending of space-time, and there was this total solar eclipse. So we had the same setup where you had the, let me show that picture again because it's useful to illustrate. So you have the same setup where you have a star that's behind the sun, but in this case we'd have the moon blocking the sun entirely, so that we can see stars, because usually during the daytime you can't see stars. So if you're trying to look at something that's close to the sun, you won't see it because it's lost.
Because it's not like we had a chronograph or anything like that. We weren't able to block out the sun that way. We had to use our own, the moon, which just happens to be at the perfect distance and radius to do this.
Yeah. So the moon blocked the sun, and so Einstein calculated exactly how far some stars would be shifted, and Eddington went out and looked for those stars in that position and found them in the right place, and that was a verification of Einstein's theory. And so this is actually
about the story, though. That was not the first attempt. There were many attempts to do this. I used to work up at the Mount Wilson Observatory, and we've talked about this, where there were many attempts to do this observation of looking at the eclipse and seeing if they can see that star, and traveling all over the world for these things. And one thing after another kept foiling it. Clouds, which is the astronomer's nightmare. Just inclement weather. I believe there was one where war was happening and they were not allowed to be where they needed to be. And finally, the observation, the experiment was able to provide ample evidence for his theory.
Yeah, so this basically made Einstein famous overnight. This was really big news when this happened, and that's what made Einstein the celebrity that he is now. That this beautiful demonstration of gravitational lensing, and so it's not just the shift in position of a star. We see gravitational lensing all over the universe, and in really big, impressive ways. So one of the things that is the coolest kind of demonstration of gravitational lensing, and one of the most useful things, is that large objects like galaxies or clusters of galaxies or even black holes can lens the light behind them, and two things happen there. One is that we're able to see like the distortion of images of things behind the massive object. but we're also so we're able to use that distortion to measure how much mass there was, because the amount of distortion depends on sort of how deep that dent in space-time is. That sort of affects how much of that light gets bent around the object.
Right.
And so you get some really cool effects. One of them is that if you have the alignment exactly right, you can get like a ring.
Or, as we've seen recently, a smiley face.
A smiley face, yeah.
A smiley face. So, I mean, so this is something that I'm totally pandering to the audience, because it's been in the news. This is something that ESA put out a few weeks back, and actually a friend of our show over at the Hubble Space Telescope, who shows up to a lot of our public talks out there, Judy Schmidt, she found this in the Hubble archive. And this is just an amazing, so first of all, a citizen astronomer going through the Legacy archive discovered this, and it's just amazing. In so many ways, it's able to convey this amazing astrophysical phenomena, but it's also something that we as humans see, we can recognize it. It looks like a smiley face. But what's going on here? What are we seeing, besides the smiley face?
So what we're seeing is there's a cluster of galaxies in the center of the image, and you see the eyes are basically part of that group of galaxies, and so there's a lot of mass there, and a lot of that mass is dark matter, which we've talked about in other episodes, and that mass is creating this dent in space-time, and the light rays from galaxies far distant behind that cluster, those light rays are being bent around. And it's a sort of spherical thing, and so they're bent around in these curves. And because they're extended objects, they get bent as, you get these giant arcs in the picture.
Right.
And there's some really nice demonstrations of that. One of my favorite things that happens where you can see that is Einstein Rings. So I have here, let me show you this nice picture of an Einstein ring that I like a lot. Yeah, the horseshoe one.
Yes.
So this is a beautiful demonstration of the Einstein ring, where you have a massive, I think that's just a single massive galaxy there. That's an elliptical galaxy, and there's a lot of mass in that, and it creates this dent, and there's this blue galaxy behind it, and that blue galaxy is stretched out into a giant ring that just goes all around. So it's a really perfect alignment. Now you have a wine glass
too.
You brought props. Yeah, I did not bring props because I don't have a wine glass. But and
if any of you follow me on Twitter, you know that of course I have wine glasses. And this one is empty, and not because I've already used it. It's a clean wine glass. Next time we're here, I will have a better use of this, because I'm going to get a cheaper wine glass and break the stem off and have a better presentation of this. But we're going to try to show something. So let me make sure the camera stays here so I don't have to worry about it. So I have an awesome galaxy. Look, it's pretty.
Very good galaxy. Yeah.
And then let me get my fingers away from the stem. And
So you can see in that demonstration, so the wine glass, the glass is bending the light, so the light is moving through the glass and being bent around, and you get this sort of circular distortion of the light. And so if the object behind is a spread out object, then you get this nice ring-shaped circular distortion of it, and you can see that in things like these Einstein rings. And it looks just like that. It's a very similar kind of lensing effect. And I have another. There's another nice demonstration of this. Do you have the? I put the animation, the lensing GIF animation in the shared folder. If you can show that one. On your screen.
Pull up which one, because I have a bunch of GIFs because I love making them.
Yeah, this one's called lensinggif.gif.
That might help. Here we go. Let me pull it up.
Okay. So this is.
Let me zoom and enhance CSI style here.
Okay. So this is an animation of what would happen if you had a black hole between you and a distant edge-on galaxy, and it shows this distortion, and it shows how you make this ring. and you get these sort of spread out pictures. Yeah. So in this animation, you can see if you had a black hole moving between you and that distant galaxy, you could see how you get the ring at certain moments, and then you get sort of multiple images if the alignment isn't perfect. And in general, it's rare to get that perfect alignment, although it does happen, and there are surveys that look just for Einstein rings.
Right.
And so you can get like a whole set of them. I'll show you. Here's a set from the Hubble Space Telescope, where you have a whole bunch of galaxies where you have a big bright thing in the center. That's the foreground, and then you have these blue arcs in the background. And they're blue because these are star-forming galaxies, but they're more distant, and the light is being
and I think that's something to point out too, is that these things are far beyond, way behind these normally elliptical galaxies, because elliptical galaxies tend to be far more massive than our smaller galaxies, and so they have more matter, so they have more mass. Yeah, and they tend to be cleaner lenses as well, like a more spherical. If you have a more spherical distribution, you get a more ring-like or sort of cleaner lensing happening. But you can also get this kind of gravitational lensing with clusters of galaxies, and there have been some really amazing images of clusters of galaxies and lensing of things in clusters of galaxies. And that's, when we're talking about clusters here, that's a big part of the frontier field. So our new initiative over at the Hubble Space Telescope is called Frontier Fields. You can visit frontierfields.org. And what that is we are using the Hubble Space Telescope and its ability to image in the near infrared and looking at galaxy clusters and using the large amounts of mass in these galaxy clusters, using the gravitational lensing to look further back into space and time than previously able to. And it's amazing. I mean, Hubble was never intended to do this in the first place. Even when they put up Wide Field Camera 3, this was not something in anyone's mind, and hey, we could probably do this. But now we're using six galaxy clusters, these frontier fields, to probe into deeper parts of the universe while also learning about dark matter at the same time.
Yeah, I mean, one of the important things to mention about gravitational lensing is that it does work as a magnifying glass. In the same way that a lens made of glass used on Earth can magnify things behind it, gravitational lensing can do that. So it can gather up light from an extended object, and it can magnify it and make it brighter and bigger. And so you can use gravitational lensing to see things that are too distant to see ordinarily. So in a sort of counterintuitive way, if you have a little galaxy behind a massive cluster, you're more likely to be able to see that little galaxy because its light can be magnified by that natural magnifying glass that is the cluster.
Well, and we have a perfect example from yesterday's press release, actually, which goes into a few things. So let me pull this up here, and we can dig into it. So this was, and let me make sure my screen gets changed. This was our big press release yesterday. We're at Hubble, where there's just so much happening here. So
there's a lot,
there's so much going on. So this is one of the Frontier Fields clusters. This is Max J1149.5 plus 223, or 2223, which is just its designation in the sky. But what we're seeing here, first of all, this is the galaxy cluster. The blue stars, these blue streaks are the galaxy behind here. This is an elliptical galaxy in front of the galaxy cluster. So this thing is actually being lensed twice, which just blows my mind. And on top of it, we're seeing a supernova that may have originally appeared to us back in 1995 in this area, but because of the way that the dark matter is distributed through here, and also the lensing going on with this elliptical galaxy, we're seeing what's known as an Einstein Cross. We're seeing 4 instances of the exact same supernova happening right here. and
Yeah.
it's
And that's
awesome. I just
yeah.
we had our Hubble Hangout yesterday about this, and I'm still just dumbfounded by how amazing the geometry had to be for this to happen.
I mean, the cool thing about looking at a supernova as that's gravitationally lensed is that you get to see it more than once. So, because let me show you another picture that talks about the different paths of light, the different paths that light travels if you have different kinds of lenses. So this is an image showing that if you have the lensing mass in between you and the distant galaxy, and if you have different shapes, then you get different kinds of lenses. So you can get an Einstein ring if you have a nicely sort of spherical mass. If you have
Can you zoom in a
mass
little
that's
bit more on that?
yeah, hold on. If you have a mass that's sort of elongated, then you can get this Einstein Cross. And if you have a
Which we
complicated
normally
mass
find
like
in quasars, right?
yeah, usually you often see quasars in that cross shape because quasars are very tiny, very small. I mean, basically, if it's a tiny object, it's very hard to make it stretched out like a ring. You just get multiple images of that tiny object.
Right.
And then if you have a cluster of galaxies and the mass is kind of distributed in this lumpy way, you get these arcs showing up behind, sort of in a sort of circular pattern around the cluster. But one of the things to notice about these kinds of images is that the light is traveling on different paths for each image, and so some of these paths are longer than other paths. So in some cases, the light gets bent quite a lot, and it takes a long path, and sometimes it's bent less, and it takes a shorter path. And what that means is that because the light is taking longer in some cases, you see the supernova later in some cases. So, so the supernova goes off, and the light is traveling to you on different paths, and one of the paths is taking a longer. It's one ray of light is taking a longer path, and so you see that ray of light later. And so on this Einstein Cross of the supernova, they light up at different times.
Yes.
So you can see the supernova happen in one place, and then maybe a few days later you see it happen in another place, and then maybe a couple of years later you see it happen in a different place because it's taking wildly different paths.
Here's one of our release videos that we did release on it, which actually shows that. So that image I just shared is, we're expecting to see another instance of that supernova show up in somewhere between 2016 and 2020. And let me just put this video up to illustrate that. So here is what we're looking at. So here's Hubble being all cute. Hi, I'm Hubble. Here's that far. So this is where we thought we saw it back in 1995. We're looking over the data right now to make sure that happened. But based off of the geometry that we know, we're expecting that this is where it was observed. However, back in 95, Hubble did not have the capabilities of looking in these wavelengths and being able to look that way, so we aren't able to detect anything from Hubble. Another thing to point out is that this galaxy that we're looking at is about 9.3 billion light years away, whereas the galaxy cluster is around 5 billion light years away. So we're talking about immense distances here.
And it's useful maybe to point out that you get the best gravitational lensing when you have the lens about halfway between you and the distant object. So that's a very good alignment.
Exactly. So when we came here and we saw late last year when it was observed, we're seeing actually at separate times is coming in that just based off of the geometry of the dark matter distribution and this elliptical galaxy, which again we're seeing in those different places, we're getting that Einstein Cross. Now, as we were talking about later, we're still expecting another instance of the supernova to show up somewhere between 2016
Which is so cool.
Isn't that awesome?
It's so cool. It is so cool. And there's another super cool thing about this, which goes into more general relativity, and I guess we'll do another episode on general relativity later. But not only is space stretched out and distorted in this kind of lensing, time is also stretched out and distorted.
Right.
And so actually, when we watch that supernova, let's say that supernova, the brightening of the star, the explosion and the dimming that takes about a week, when it happened, we see it take 2 weeks. It takes longer when we see it because it's been stretched out by the expansion of the universe and by going through this gravitational lens thing, and so we see it in slow motion.
And that's what we're seeing right now is that supernova is getting brighter right now. We're at, like the observation is showing that what we're observing right now is still getting brighter. So we're watching this in like freeze frame. Like, so your iPhone 6 can't do this. I'm sorry, but I mean, imagining having a supernova go off and you having this super high speed camera and then playing it back at regular frames per second. That's essentially what we're doing here is with that time dilation, is that we're just seeing more of it. It's being dilated. And so though this happened billions of years ago, we're able to slowly see the progression of the supernova happen.
And we have...
And we get to watch it again.
Yeah, we have advanced warning. It's like instant replay. Like we're getting astrophysical, real instant replay of an exploding star. Like, it happened once, and we were like, oh, that was amazing, and it's like, let's watch it again. We're watching it again in slow motion.
So yes, we now have a sports ball reference to some astrophysics, and we will get instant replay. And talking with the astronomers that were working on this from Johns Hopkins and Caltech and UCLA, they are going to be putting in for some more Hubble time to hopefully observe, because right now, because of the limitations of Earth-based, and having to look in IR can't really do that from the ground. You have to be able to look at it from space, and right now Hubble's the only thing that's really going to be able to do that. So they're putting in for more time to hopefully. I mean, could you imagine being able to watch the entire supernova happen in slow-mo from start to finish when we've already seen it, and now we get the full story? That's just awesome.
It's very cool.
On a 25-year-old instrument, nonetheless. A 25-year-old spacecraft. That's just... And I'm looking down, and we're actually out of time. We're actually a little bit over.
No.
I know, we do this all the time.
Can I show just a couple more super cool cluster images?
Absolutely, and then I'll also do some shout-outs to people that have been tweeting at us and making comments.
So this is another galaxy cluster doing lensing, and this one I love because you've got this blue star-forming galaxy. So it's a counterintuitive thing that some of these distant things are blue. Part of the reason they're blue is that they're young, and young things have a lot of young stars, and they're blue, and they're so far away. They're very early universe. They're young and they're bright, and that's why they're blue.
Which we will actually touch on when I post the next Pint in the Sky later tonight.
Yes. So these things. So there's like one blue galaxy, star-forming galaxy, and it shows up everywhere in this picture because it's being stretched out and multiply imaged. So you've got it here, you've got it over here, you've got it spread out, like smeared all over this image.
It's like a cosmic photobomb. He's like, I'm everywhere. Look at me.
Yeah, and this is just absolutely beautiful. This is a cluster called CL0024. This imaged by the Hubble Space Telescope.
Yes.
I really love this picture because you can really see that distortion. You can see other arcs, some of which may be that galaxy, some of which may be other galaxies, but you can totally see where that thing shows up, and it contrasts really well because the cluster is full of old red galaxies, and they're red because they're old things. They're old stars, which tend to be redder. They're elliptical galaxies, and so you get these sort of blobby red things, and so the contrast with the blue young star-forming galaxy is really strong. And then, let's see, I have another really great one here. Let me show you that one. Hold on a sec.
Well, and while you pull it up here, I'm gonna answer a question real quick here from Michael Jobin. So why do we think that heat is not doing this lensing? I see a lot of heat bending on my car, and what you're actually seeing there is, I mean, we're looking through pretty much a vacuum with some dust and stuff like that. Why is Michael seeing that wavy thing going on.
Well, it's a very similar kind of thing. So the heat is a different. It's a different density of the air. It's changing the properties of the air, and so that bends light through the air. We're seeing the bending of space-time, and that's bending space, and then the light is going through that bent space. So slightly different things, but it's a very similar concept.
Right.
So I just want to show you this image here, which is another Hubble Space Telescope image of lens stuff, and this one
because Hubble got you.
You have this, yeah. So now here you've got this sort of pinkish galaxy that's spread out and just ridiculously distorted.
Right.
In the edge over here, and that is just beautiful. And if you look around this image, you see a lot of these sort of partial rings or sort of partial arcs. Mm-hmm. And we'll talk actually next time, I guess, if we're to talk about weak gravitational lensing, about how you can use the fact that a lot of these galaxies are just a little bit distorted. They're just a little bit sort of bent to be sort of going along that circle, and you can use that also to measure masses of things in the universe. And that's another big part of gravitational lensing, is it measures the total mass. So if you have something that is dominated by dark matter, which you can't see, but that contributes to a lot of the mass, you can measure how much dark matter is there by how much gravitational lensing there is. You count up all the light matter, and then you look at the gravitational lensing. That gives you a total mass, and that tells you dark matter has to be there. So that's another cool aspect of gravitational lensing, is that it's really good as a sort of cosmic scale, like to weigh things in the cosmos. Yeah. All
right, so I'm going to do some quick shout-outs here. Judy, whom I mentioned earlier, Judy Schmidt, is watching, and I want to point out one of her comments, which is really good. It's really striking how blue the star-forming background galaxies are. In contrast to the foreground ellipticals, even with redshift, they're still really blue.
Yeah, and that's for a lot of times very young galaxies, very bright young things that haven't been. They're in the early universe. They haven't had their stars all mixed up into ellipticals. They haven't lost all their gas. They're burning through this gas, and they're really bright, and they're this blue thing. Whereas clusters galaxies, in clusters, all the galaxies are kind of mixing together, and they're getting ellipticized. They're becoming elliptical galaxies.
I ellipticize.
Yeah, and they lose their gas, and so they don't form new stars, and they have these older, redder stars. And so there is that really great contrast, which is nice, because then you can see, you can really see that these things stand out.
I'm just going to do one last quick bunch of shout-outs from everyone on Twitter that have been watching. Jeff McKenzie and Dave Grundgeiger, and let's see here, Wonky Square. Thank you, Wonky Square. And a bunch of other people that have shared out, retweeted. Thank you for doing that. Again, this is not the final version. We will actually come back in around 2 weeks' time, I believe. If you're
something like that. Yeah.
Okay. So in about 2 weeks, we will have episode 2 and maybe an episode 3, because we love talking about this. So if you want more of this, please subscribe to Know the Cosmos or at youtube.com/user/know the cosmos, all one word. And you can also see it. It will be up tomorrow at knowthecosmos.com. Mm-hmm. I am Scott Lewis, so you can follow me down at Scientific Scott right there. And my amazing, fantastic astrophysicist friend, Dr. Katie Mack, where can we find more of you?
Well, I'm on Twitter at AstroKatie. I'm also on Facebook at facebook.com/AstroKatie. I don't post there as often, but I do put up a lot of things that were, like things I'm doing on the radio or videos or whatever, so you can often find a lot of stuff there, and you can chat about it. And I'm on Google Plus as +Katie Mack.
Yep.
I recently got into Tumblr, so I have a Tumblr thing on AstroKatie. I've only got one post, but it's about sort of science in everyday life, so you can check that out. I believe that's just AstroKatie, like tumblr.com/AstroKatie or something like that. Or
I think it's astrokatie.tumblr.com.
Yeah, that one. Anyway, so you can find that. Yeah, mostly Twitter. So hang out with me there.
Yeah, mostly Twitter. I'm over on Google Plus, as most of you know me from, and I'm also I have become an addict of Instagram. I apologize to all of you that follow me for my food posts and selfies, but if you want to follow me on Instagram, I'm Real Scott Lewis on Instagram. Again, thank you. Yeah, go ahead.
I'm actually on Instagram too, but my Instagram posts are mostly not science. It's just like travel pictures and clouds, lots of clouds. So if you want to see my pictures of clouds, I'm at It's Academic Nomad on Instagram.
Nomad. Right.
Yeah.
All right. Well, again, thank you everybody for your great questions and comments. I've taken note of any questions that we have not been able to get to today, and we will try to incorporate them next week. If you're watching this later, leave comments below on YouTube, and I will go through them, and we'll either reply via text, or we'll try to incorporate them into another show. Also, if you have another idea for a show for the future, which we already have some ideas lined up, but if you have something that you have interesting, please let us know. Shoot us a tweet, leave a comment, something. Let us know. We're on the interwebs, and we'll be more than happy to talk about topics. So, again, thank you all for watching, and we'll see you in 2 weeks.
Yeah. Bye.
Bye.